This is the Building Automation Monthly Podcast with Phil Zito, episode 168. Hey folks, Phil Zito here, and welcome to episode 168 of the Building Automation Monthly Podcast. In this episode, we are going to be continuing our series on how to control HVAC systems with a building automation system. So in the previous two episodes, we looked at room side systems, VAV boxes and all the concepts associated with them. And in the previous episode, we looked at different airside systems. So in this episode, we're going to be looking at hydronic systems, specifically chilled water and hot water systems. Now, as I've mentioned in the past two episodes, this episode is sponsored by our Control Sequence Fundamentals course. If you are a building automation professional and you need to get up to speed with HVAC, but the idea of doing a stint in a trade school or spending time as a mechanic just does not excite you, and you're like, man, I've got to figure out this HVAC stuff if I'm going to succeed in building automation. Well, Control Sequence Fundamentals is the answer to your problem. It will teach you everything you need to know in order to take HVAC sequences and translate them to control concepts. So you will learn how HVAC systems work, how sequences work, and most importantly, how to control these systems utilizing a building automation system. So if that is something you are challenged with, if you are trying to figure out HVAC and you want to do it as fast as possible, and you know it's what you need in order to succeed and grow further in your career, then I encourage you to go to buildingautomationmonthly.com/168, scroll down to the Control Sequence Fundamentals logo and click on the logo. Check out the course syllabus. You'll see how in-depth the course goes, and then enroll in the course. Like all of our courses, this course is fully online, on demand, and comes with lifetime access to the course lessons. Alrighty, so chilled water systems. So how we're going to do this is we're going to go through chilled water system concepts, then we're going to look at air-cooled chillers, we're going to look at water-cooled chillers, and we're going to look at partial loading of chillers. Then we're going to move through the hydronic system concepts on hot water, and we're going to look at hot water system concepts, single boiler control, multi-boiler control, and then steam. So a lot in this episode, probably going to go over the 30 minutes that we normally aim for, but who knows, we may be able to cram it into that time constraint. So chilled water systems. So whenever we're thinking of chilled water systems, we first have to get clear on some terminology. And so we're going to focus in on a couple key terms that you've probably heard if you've been in this field for any amount of time, but you may not know exactly what they mean. So we're going to focus in on the condenser side and the evaporator side of a chiller. We're going to talk about load. We're going to talk about lift. We're going to talk about tonnage, and we're going to talk about FLA, also known as full load amps. So with chilled water systems, what is going on is that we are focused on two key concepts. One is heat removal, better known as BTU removal. We are taking energy out of the building, and we are utilizing the refrigeration cycle to do it. Now, the refrigeration cycle is something that we utilize in rooftop units. I talked about them, how we have DX cooling, and we utilize DX cooling, and it has some concepts, but I didn't really go into the refrigeration cycle in previous episodes. So what is this cycle? Well, quite simply, it's a way of transferring heat from one source to another source using science. I mean, there's more to it than that. Don't worry. So what happens is we have an evaporator side, right? And we have a condenser side. Now, what is going on these quote-unquote sides of this loop is that the evaporator side, right? This evaporator side, it absorbs. So it is going to be absorbing heat. Now it's absorbing heat, and it is then taking that heat, right? So it's taking that heat and passing it to the refrigeration. So the refrigeration is going to change states, and then the refrigeration, now heated up, is going to go into the condenser. And the condenser then is going to take the heat that's in the refrigeration and pass that to condenser water. Now that condenser water is going to be heated up, and it is going to then transfer that heat out to the atmosphere utilizing what is known as a cooling tower. Now that's on water-cooled chillers. On air-cooled chillers, it's basically the same thing, minus the cooling tower. You now have some fans that are pulling air through this condenser coil, or you're just using natural airflow. This is why it's bad to put air-cooled chillers in a corner surrounded by 8-foot fences next to a building, because you want to keep them quiet, but now they're not getting any airflow and they can't really transfer heat as well as they should. So yeah, if you've ever wondered about why that's bad. But like I said, what's going on with this refrigeration cycle is that because refrigerant changes state at different temperatures and pressures than water, what we're able to do is actually take usually anywhere from 8 to 12 degrees out of a primary chilled water return loop. And so we take that temperature, those BTUs, we transfer them to the refrigerant. The refrigerant changes state, and then the refrigerant goes into the condenser. Now, I know I'm skipping compressors and I'm skipping expansion valves and things like that. My purpose here is not to teach you step by step of the refrigeration cycle. It's rather to help you understand the concepts of evaporators and condensers and BTU transfer. That's the most important thing out of this. If you take anything from what I'm about to tell you over the next probably 2 to 3 minutes, it's understanding how energy in the form of BTUs, in the form of heat, is transferring throughout a building from a systems perspective. You're thinking about this air handler, and it's got a cooling coil, and you've got this airstream, maybe a return airstream, coming into the cooling coil, and then that cooling coil has chilled water, and that chilled water is absorbing heat out of that return air path, and then that discharge air path on the leaving side of the coil is now colder, but the water leaving that coil is now warmer, and that warm water, as I said, returns to the evaporator. The evaporator transfers that heat to the refrigerant, which then goes through the condenser coil, which transfers the heat to the condenser loop, which then takes that hot water, warmer water, and takes it through a cooling tower, and that cooling tower in turn actually goes and lowers the temperature of the water using evaporation, typically using evaporation. And what's going on then is now that cooler water returns and can absorb more heat. And that is how water-cooled chillers work. And we'll talk more about that. So as I mentioned, we have air-cooled and we have water-cooled chillers. Now, air-cooled chillers, they simply transfer the heat directly to the air from the condenser coil. Now, when we are dealing with this, as I mentioned, we need to be aware of airflow and solar load. Now, as a BAS professional, you typically can't pick where a chiller is going to be placed. So your ability to influence airflow and solar load are going to be low. However, if you are trying to troubleshoot design day issues and you notice that a chiller is surrounded by 12-foot solid fence and it's in 100% sun almost all the time, then you can see that there is likely to be airflow and solar load issues in these design days. And recall that I said in design days in previous episodes are days in which you are going to be at or exceeding the capacity of the designed system. So these aren't going to go and dramatically affect the air-cooled chiller efficiency on normal days, but on these design days, they can have a large effect. Now, water-cooled chillers are typically larger tonnage, and we'll talk through what tonnage is a little later in this episode. But they're larger tonnage systems, meaning that they have a greater capacity to remove heat from the building, and they consist of several systems that all come together to create a full chilled water loop. Now, what goes on is you have the chiller, you have the chilled water side, you have the condenser water side, you have cooling towers, you have cooling tower fans, you have tower bypass valves, and you have heat trace. So all of these systems are being utilized to remove heat from the chiller through the use of evaporation at the cooling tower. So cooling towers are typically these big stacked up units. You'll often see them in some climates putting off steam depending on the temperature of the outdoor air. And what happens is that you either got water flowing through them, flowing over them, or you're using some form of plate heat exchanger that may just be transferring directly to atmosphere. And you can use these in partial load conditions where you have to run for process loads. Now, process loads are things like IDFs and MDFs that you may be having to go and run temperature or get heat rather out of those loads and transfer them out, but they don't require running a complete cooling tower. Now, in a flow-through scenario, you are going to simply flow the water through the basin, and the evaporative effect of air moving across the surface of the water will remove heat. In flow over, you will actually let the water rain down, essentially, into the tower, and this is a very simplistic example of cooling towers right now. So realize there is more to it. Now, in certain environments, you are going to have to run the cooling towers and the condenser loop regardless of the outdoor temperature. And so that is where heat tracing comes in. And this is basically a form of heat, usually by an electric coil that helps keep the piping from freezing. Now, it doesn't always... or rather, it isn't designed to go and keep something in, negative 50 temperatures from freezing. However, it is designed in lower temperature situations where you may, for some reason, have to run water, or you have residual water in the piping and you want to keep it from freezing. There's a lot more to heat trace that I'm not going to cover here, but realize that it is something, especially in the more northern climates, that you need to be aware of as a BAS professional. It is typically a DO and BI contact that you will be controlling or at least monitoring with your building automation system. Now, tower fans, they can be constant volume or variable volume. Now, the nice thing about variable volume fans is that you can go and actually partially load towers. You can run multiple towers in unison at partial speeds, taking advantage of that fan curve so that you're optimizing your efficiency while controlling temperature. Now, whenever you're dealing with cooling water fans, you are going to be controlling to a condenser water set point, and that set point is actually going to be driving your fan speed. So you're typically going to want to have a medium speed loop in order to run that. Now, the other thing I want to talk about here before I kind of get into air-cooled chillers and water-cooled chillers and how to control them and sequence them and stuff is two concepts that a lot of folks still don't really understand, and that is lift and load. So you oftentimes will hear these terms used, and sometimes folks will use these terms and they'll be using them incorrectly. So the easiest term is load, and it's a percentage of the performance of a chiller. So it's how much is the chiller loaded. It can be calculated manually. I'm not going to take you through that pain, but it is most often calculated by the chiller. Now, this is not to be confused with FLA, which is full load amps, okay? That's really important that you realize that, because loading can be a calculation that's just based on a percentage, and it's looking at either temperatures or it's looking at the refrigerant, or it can be FLA. There's a variety of different ways load can be calculated. There is the mathematical equation of load, which is looking at temperatures and tonnage and calculating your tonnage versus total tonnage, and that creates a percentage. But realize that sometimes load does not mean the same thing. So you always want to clarify what load actually is when you're talking to someone. Lift is much easier. It's simply the difference between the condenser refrigerant pressure and the evaporator refrigerant pressure. And so this is a measure of efficiency. You want to go and try to control this so that you are being as efficient as possible with your pressurization of refrigerant as part of the refrigeration cycle. There's a couple different ways you can do this. You can be adjusting temperatures. You can be running different condenser temperatures, but those are some more advanced concepts that are really out of the scope of this podcast. All right. So I guess one last thing I want to cover here before I move on is I'm on the fence about this, to be honest. I'm like, do I want to? Yeah, I'll cover this anyways. I know I just literally said that it's more of an advanced concept, but I feel like I should explain lift a little bit further, because it's something that, especially on larger tonnage, can have a decent impact as far as efficiency and how you're running your chillers. So, in an ideal world, you would lower the lift and it would have the compressor working less, because there would be less refrigerant that would have to be compressed. Okay, right? The compressor compresses the refrigerant, and if the refrigeration pressures are kind of equalized across the condenser and the evaporator, then you have to go and lower. You don't have to go and run the compressor as hard. Now, this can be achieved by simply having the lowest entering chilled water temp, and by having a lower entering water, the refrigerant, and ultimately the compressor does not have to transfer. Now, when I say entering chilled water temp, that's chilled water return. So whenever you hear entering chilled water and leaving chilled water, that's entering the chiller and leaving the chiller. So if someone tells you, hey, entering chilled water temp is this used to confuse me actually when I was first new to this trade. Folks would say the entering chilled water temp, and I was like, oh, entering the building or entering the chiller? Well, it's actually entering the chiller. So it's chilled water return temp. And if you can have that lower, then you don't have to transfer as much heat to cool the leaving water. I mean, that makes sense, right? Because if the chilled water return temp is closer to the chilled water supply temp set point, then you're going to have to run the compressor less to go and kind of get that heat over to the condenser side where it can be evaporated by the cooling tower. Now, in the real world, going and doing this is a whole nother matter. Now, you can do this by utilizing economizer within your air handlers, making sure you're maximizing the use of economizers, but then you introduce issues like, should we be driving an economizer based off of dry bulb or enthalpy, because are we introducing a bunch of moisture into our building, which takes a bunch of energy to remove anyways? So you can kind of see the circular logic here, and one of the reasons why I was hesitant as to if I wanted to explain this or not. However, on the simplistic side, in climates that are more drier, not talking climates like Louisiana or Florida, but climates like Arizona, things like that, this is somewhere where you can take advantage of that. Granted, they have less months when you could actually use an economizer because it's so freaking hot out there. But By going and utilizing economizer, by raising discharge air temperature set points on air handlers, you're able to reduce the demand on the secondary or primary chilled water loop, thus reducing the delta, the difference between chilled water return and chilled water supply. I really hope that makes sense. I know it's kind of a more advanced concept, but it's an important one, especially when you get to really large tonnage plants. So as I mentioned, we have load, and load is going to be probably the most important setting whenever you want to do staging or partial load control. So a lot of what you will do, if you're going and you're new to this trade and you have to control air-cooled chillers, it's relatively simple. I would say it's on the complexity of controlling a packaged rooftop. It's just not that hard. Now, what gets difficult is when you start to have to control complex dual chiller plants that maybe are using a decoupler, and you're calculating primary GPM and secondary GPM and trying to figure out when is the loop reversed and when is it flowing through the coupler versus being drawn back through the decoupler, all those kind of concepts. And load is a concept that you will use extensively when you are staging chillers. So typically in a staging scenario, you're going to wait until you're 90 to 95% load, or FLA. And what will happen is you will stage on another chiller, and then you let the chillers drive to the chilled water supply temp. Now, the chillers typically will then be staged down once they hit 30%. Anything below 30% load, and you're getting really inefficient with the chiller. Ideally, chillers, depending on their efficiency curve, anywhere from 55 to 70% is what I've heard. I'm not an expert when it comes to efficiency curves on chillers. I don't profess to be, but it's easily something you could Google. You could Google, just like you can Google fan curve, you can Google chiller curve and see where they're most efficient as for their loading. And that's where you stage them up and stage them down. And now you get into this scenario, though, where you hit this 30%. And running a centrifugal chiller at 30% or below is really inefficient. And this brings in partial load chillers. Now, these are typically chillers that have multiple stages built within them. You'll typically see this maybe in an air-cooled chiller that's sitting outside, and this will handle smaller tonnage. Now, like I said, we're going to come back to what tonnage is. So tonnage, quite simply, is a rating that is essentially saying, hey, for this 1 ton of cooling, you can take 12,000 BTUs. All right, so 12,000 BTUs is going to equal a ton. Now, if you've been working with air handlers, this should be fairly familiar to you. You've heard of, kind of the rule of thumb, 350 square feet per ton of cooling, and looking at 12,000 BTUs, and you can look at your coils and you can calculate their transfer rates, and you can figure out what you need as far as tonnage. But there is a real simple calculation in order to calculate tonnage. And so for those of you who are interested, here it goes. So what you do is you go and you have to first calculate your temperature differential, right? So you're going to calculate what would be the incoming water temperature and the required chilled water leaving temperature. So the entering temperature and the leaving temperature at full load. All right, then you're going to look at your gallons per hour times 8.33 times that delta T that we just calculated. All right, that's going to give us our BTUs per hour. All right, so then we're going to take those BTUs per hour. We're going to divide them by 12,000, and that's going to give us our tonnage, so our cooling capacity tonnage that we're required. And then kind of the rule is that you want to oversize a chiller by about 20%. So what you would do is you would say, all right, I want to go and take that 20%. And so I would say whatever that tonnage is times 1.2, which is 100% plus 20%. So that's 1.2, that's 120%. So just to recap, you take the delta of the return versus supply temperature, you go and times that times 8.33 times the gallons per hour, that gives you your BTUs per hour, divide that by 12,000, and then times it by 1.2, and that should give you your tonnage for your central plant. Now, that's your overall tonnage, but as you start to go and hit low load situations where maybe that delta is such or the gallons per minute is such that it is reducing the required tonnage, that's where you use this partial load chiller. Now, why did I take the time to actually go through explaining this to you in this level of detail? Well, the reason I did that is because I feel like when you understand how these calculations happen and what actual partial loading means and why it matters, that it makes your ability to control these systems that much greater. Because now we realize the reason why we are using a partial load chiller is because it's more efficient. And the reason we have partial load is because either our GPM or our delta T has varied. So we understand that those are the two variables that are going to be impacting the tonnage required of cooling by our building systems. All right, and I'm looking at the time here, and I'm realizing that there is no way I'm going to be able to do hot water as well in this episode because we are already 28 minutes in, and yeah, we're not even full or finished with chilled water yet. So the last thing I want to discuss is variable speed drives, which these are basically like fire rates for chillers. So if we think of boilers having adjustable fire rates, chillers vary the speed of refrigerant flow using variable speed drives. Now, when you go and vary the speed of refrigerant flow, what's going on is that you're varying the amount of heat that is absorbed and exhausted from the building's chilled water return out to the condenser water supply and then through the cooling tower loop. So you can have these variable speed drives attached to the compressors of the chillers. And that is something that you will see on a lot of large tonnage centrifugals. This really allows them to be more efficient across partial loading. So it really helps them to do that rather than having to run full on balls out for the entire load spectrum. You can actually vary how hard the compressor is working when there's situations that don't deem necessary a fully loaded chiller. Does that make sense? I hope it does. All right, so moving right along, let's dive through air-cooled chillers. So as I mentioned, we've got pretty much all the concepts down, right? We've talked through lift and load. We've talked through partial load. We've talked through how the refrigeration cycle works. Now we've got these air-cooled chillers. Now, when you're dealing with air-cooled chillers, and this will be true for all chillers, not just air-cooled chillers, you have to realize that when you're enabling a system, you first have to make sure, just like with dampers on air handlers, you have to make sure there's a path for flow. The worst thing you can do with a chiller is enable it and have no water flow. The second worst thing you can do is enable a chiller, or not enable the chiller, but enable a pump and have a valve closed. That's called deadheading a pump. Now that will eventually wear down your pump, and running a chiller without any flow to it will start to wear down the chiller. So the first thing we want to do is open up our valves, make sure they're open, make sure we've got water flowing through, and at that point we can enable the chiller, and after that chiller is enabled, we can enable the temperature control. That's why I often, when I'm programming chillers, I like to have a system enable and a chiller enable. System enable will actually enable that process of opening the valve, turning on the pump, proving flow status, and then the chiller enable will actually be part of the system enable sequence. And only after all of these are done would I actually move into temperature control. Now, temperature control is typically driven, and this will be consistent for water-cooled chillers as well. It's typically driven off of three variables: either schedule, you're scheduling a static temperature, you're doing a load calculation in the building and doing a reset of supply temperature, or you are resetting it based on outdoor air. Yes, there are outdoor air resets for chilled water. They're not that common, but they do exist. Load is becoming a more common reset, and scheduling just, hey, it's on and it's going to run 42 all the time. That is one of the most common ways of running a chiller. All right, now that you've got that down, in order to do water-cooled chillers, you simply need to remember it's the exact same thing, right? We need to make sure our valves are open, system gets enabled, and then we turn on our pumps, and then we turn on the chiller. But we also have this new thing called the condenser side. So now we have cooling towers. And with cooling towers, we can go and we can have water flow through the tower. We can have it flow over the tower. We can control variable fan speed on the tower. So what we want to do is we want to go and look at what we are trying to achieve with our cooling tower, and we want to control it to achieve our approach and our range. Okay, so range is simply the difference between entering and leaving condenser water. That's pretty straightforward, right? And if that was all we had to control, it would be relatively simple. If there were no humidity in the air, and all we had to do is take the energy out of the water and transfer it to the air, and this air was 0% relative humidity, it had no moisture in it, our job would be relatively easy. But realizing that air has moisture in it, we actually have to deal with what is called wet bulb. So wet bulb is going to be the lowest temperature that can be reached through evaporative cooling when the air is not dry. Okay, so dry bulbs are traditional temperature. Wet bulb factors in the effect of moisture in the air. So our approach is quite simply the difference between the leaving condenser temperature and the wet bulb. So if I were to tell you we want a 7-degree approach from a specific temperature, we are saying we want the wet bulb to be 7 degrees below that temperature. So why does that matter? Okay? Well, remember the definition that I had. The lowest temperature that can be reached through evaporative cooling when air is not dry. Okay, but here's the deal. If we need the air to be at a value low enough to support evaporative cooling, because that's how cooling towers cool, then what's going to go on is that when we have a high wet bulb, we're going to have a low approach, which means the point at which we reach saturation on that temperature is going to be closer. So we're going to have, so we have that range, but the effective range inside that range, known as the approach, is going to be smaller. So we're really going to be working with less air that we can transfer, or rather we can transfer less energy to the air in the form of moisture. That's why cooling towers will tend to operate more efficiently in drier climates and less efficiently in very moist geographies. So with that being said, if we want to go and control this cooling tower, and we want to make sure that we're being efficient, then what we need to do is that we need to be aware of it, and we need to realize that in moist areas, we may have to go and run our chilled water temperatures at higher temperatures because we simply cannot get the transfer that we could get if we had a lower amount of moisture in the air. It's simply not possible for us to transfer heat because the air cannot absorb the heat. So this is something that is true for very humid areas, but it's something just to be aware of. You may not ever run into it, but if you ever do work in a really humid area, just realize that this may actually go and stump you at first. You may be like, why am I not able to get the exchange I should be able to get? All right. So as I mentioned, we have cooling tower controls. Now, with cooling tower controls, when the condenser water is at or below set point, we can bypass the tower, disable the fans, and just run the water in a loop. Now, as the temperature rises, we will typically go and have the flow go fully through the tower, okay? And this means through the basin of the tower. Now, as the temperature continues to increase, we will typically turn on the tower fans and send water over the tower. We're taking advantage of the evaporative effect by doing that. So that's the big thing we need to realize when we are controlling water through the tower. Now, there's all sorts of things of water starvation and unequal sumps and things like that. I'm not really going to dive too much into that. The last thing I want to cover in this episode, because I realize it's getting a little long in the tooth now, is that lead lag and partial load control. So lead lag is quite simply rotating pieces of equipment so that you don't run them constantly so that they have a longer life. Pretty straightforward, right? And you can also use lead lag when something fails. You go over to the lag, and you could do this for chillers, for cooling towers, pumps. You can run lead lag across the spectrum of all these systems, right? Now, the one thing we have that is really different from hot water systems, and we'll discuss this in next week's episode, is with hydronic chilled water systems, we have partial load. Now, typically how we go and run partial load is that when load is lower than the range that a single primary chiller could efficiently handle, and when the load is higher than all of the primary chillers can handle, that's when we tend to use our partial load systems. They are typically independent of a primary system, meaning that they will typically have their own pumps, cooling towers, and valves that are sized to them. That way they can run independent, because if you were trying to run them off pumps and valves and towers that were sized to a primary chiller that was maybe 1,000 tons, and this is a small little 200-ton chiller, you could go and overload the system. That's why they typically have their own pumps. So folks are often wondering, why do the little, partial load chillers have their own pumps, their own towers, etc.? It's because of this exact reason. They're designed for a lower tonnage, thus less GPM. So with partial load, the big thing to remember is that it is used in two scenarios. One is lower than a single primary chiller could efficiently handle, and when the load is higher than all of the primary chillers could handle. I know this was a lot. I know that in episodes recently, we've been going a lot deeper on the technical side of things. What I've been trying to do is, I realized that HVAC was just an area that a lot of folks are weak in. I really wanted to help out in that area. I feel that this is one of the things that has really helped me be very successful in my career. And I feel that if you know it as well, it'll really help you take your abilities and skills to the next level. So with that being said, that completes this week's episode. Thanks a ton for listening. Like always, you can go to buildingautomationmonthly.com/168. And you can go and find out about our Control Sequence Fundamentals course. If you found these episodes interesting and intriguing, I want to tell you we go into a lot more detail. And quite honestly, it's a lot better organized than our podcasts in the course. So I would really encourage you to go and check out Control Sequence Fundamentals And you can find that at buildingautomationmonthly.com/168. And like always, if you have any questions, feel free to go ask those and anything else in the discussion section below the video or podcast, depending on where you're listening to this. Thanks a ton. Take care.